Boosting weak and strong learners, but many weak learners can be made into a strong learner if we do so by voting. So here's an example. Suppose there are 10 faces that are either happy, class 1, or sad, class 0. And suppose this is the gold standard. This is the right answer, if you want to think of it that way. So these are the correct labels for these faces. And suppose 9 learners are asked to classify faces as either happy or sad, 0 or 1. So the first learner has these labels. That's what they say. Notice that the first one they say is happy, and the second one is happy, and so on and so forth. And you can see that actually all of them, he says, are happy, except the last one, which he says is sad. Notice that's an accuracy of 0.6. He missed the first one, and the third one, and the fourth one, and the seventh one. Learner number 2, this is her choices for sad and happy, and she also has a 0.6 accuracy. So she missed the third and the fourth and the 7th and the 10th, and so on and so forth. So each one of these has rated the faces based on sad or happy, and they all have an accuracy of 0.6, except the last two have an accuracy of 0.5. But notice that if we take them all together, notice that in the first column, we have 6 to 3 for 0, and that's correct. In the second column, we have 4 to 5 for 1, that's correct. 5 to 4 for 0, correct. 5 to 4, 0, correct. 4 to 5, 1, correct. 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 That is, when we take them all together, they're perfect in their prediction. So why did this work? Well, the weak learners were wrong in a wide variety of ways. Let me show you a simple example. So here we have 3 learners and 3 observations. Suppose the first learner gets the first observation wrong, but the other 2 right. The second learner misses the second observation, but the other 2 are right. And the third learner gets the last one wrong, but the other 2 right. That means each one of them has an accuracy of 2/3, which is about 0.666. But if we take them all together, then for the first observation, we have a wrong and 2 rights. That's correct. And then 2 rights and a wrong. That's correct. And again, 2 rights and a wrong. That's correct. So corporately, voting led to perfection. The key is that the errors are independent and they all participated equally. So we're going to develop this intuition into a concept known as boosting as a special way of voting. So suppose we have training data of the form T sub I, C sub I. The T sub I's are instances of the features labeled by class C sub I. Positives are in class 1, negatives are in class -1. Suppose we have V classifiers. Y is the V of X, where V equals 1 to V. And remember, each prediction is either positive or -1, and voting is a summation over V. So in our voting scheme, if the vote is positive, then we'll predict that the ith observation is positive. If it's negative, we predict the ith observation is negative. However, random classifiers could cause the votes to also be random. So we generalize the voting scheme so that each classifier or voter has a weight, alpha V, and they vote with this weight. Remember, these y's are in negative 1, 1. So some terminology. Each individual classifier is a weak learner. Voting leads to what's called a strong learner. In our case, the strong learner as a function of x will be the sign, positive or negative, of the weighted vote, weighted by the alphas of v. Our goal is to combine weak learners into a strong learner. The weights, alphas of v, should be related to the training error. Weak learners should have independent errors. And the question is, how do we select learners and weights alphas of v? So 0, 1 loss is sufficient, but remember it's not differentiable. So we approximate with an exponential loss. It's crude, but it is differentiable. So therefore, boosting minimizes the error, the loss, e to the negative c sub I y strong t sub I on the ith observation in the training set. And the cost is the sum of the losses. So here's how it works. The key is we're going to implement this dynamically, which means successively. So assume we already know y1 of x up to ym minus 1 of x, and that we know the weights alpha sub 1 up to alpha sub m minus 1, where alpha sub v is greater than 0, because we don't want to flip the sign of y sub v. The goal is to find the next, the mth learner, and weight alpha sub m, y sub m of x. So we're assuming we know up to m minus 1. We're going to use that to find for case m. So we let f sub m minus 1x be the linear combination with the alphas of the ones that we do know. And when we add all these together, that means that our total cost is the sum, I equals 1 to capital T, of the exponential of negative c sub I, f sub m minus 1, t sub I, that's what we do know, and plus alpha sub m, y sub m, t sub I, that's what we want to find out. We know this. We want to figure out what that should be. So we have our total cost, and the exponential is got an exponent of a sum, and we split that into two exponentials. And then we're going to let w sub I m be e to the negative c sub I f sub m minus 1 t sub I. Remember, we already know w sub I m because it's defined by the things we already know. So e is the sum, I equals 1 to t, of w sub I m, e to the negative c sub I, alpha sub m, y sub m, t sub I. And that's what we don't know. We want to figure out what that is. So notice that I can rearrange the exponent, and I get a c sub I, y sub m, t sub I. And if we have a match, c sub I, y sub m, t sub I is 1, and if we have a mismatch, it's negative 1. So we can split it into two parts, where c sub I is equal to y sub m, t sub I. We'll get an e to the negative alpha m times the sum of the wi sub comma m. But where there is a mismatch, we'll get a change from alpha, negative alpha m to alpha m, because that product will be negative 1. Now we're going to let chi of some condition be 1 if the condition is true and 0 otherwise. So if c is not equal to y sub m of t sub I, then chi of the condition of not equals is 1, and chi of equality is 0. Remember, this is if the condition is true, we get 1. If the condition is false, we get 0. If c sub I is equal to y sub m t sub I, then 1 minus chi of this condition of not equals is equal to 1, because the condition of not equals is 0, because we're in the case where the two are equal. So now we can use this to rewrite our sum. So we have this sum over i's and j's where we have matches and mismatches. And we can write that instead using our chi's both as sums I equals 1 to t. So it's just a clever way of rewriting the sums that we had above. And notice we've switched the order. We've put the exponential to the negative alpha sub m term at the end. So we have our total cost, e to the alpha m, times that sum with condition c sub I not equal to y sub m t sub I, and then e to the negative alpha sub m, and then another sum. Notice we've got a 1 minus chi c sub I not equal to y sub m t sub I. So we can distribute and split this up into different parts. And notice we've got a chi c sub I not equal to y sub m t sub I in both of these sums. And when we put those together, we'll get an e to the alpha m minus e to the negative alpha m times that common I equals 1 to t, w sub I comma m, chi of that condition. And then what we have left is e to the negative alpha m times the sum over the w sub I m's when we multiply that by that 1. This last term is constant with respect to ym. There's no ym's there. So recall that alpha v should be greater than 0 because it should not flip the sign of the associated learner. So therefore, we get e to the alpha m minus e to the negative alpha m is greater than 0 if alpha sub m is greater than 0. And that means that the best y sub m minimizes I equals 1 to t, w sub I m, chi of the condition c sub I not the same as y sub m of t sub I. We'll define epsilon sub m to be this sum over that condition. And now we can write in a simple form, e is e to the alpha m epsilon sub m plus e to the negative alpha sub m 1 minus epsilon sub m. Now the minimum of e occurs when alpha sub m is 1/2 the log of 1 minus epsilon sub m over epsilon sub m. And now we know how to make v weak learners into a strong learner. We assume that we've already done that up to m minus 1, and then to choose the next learner, we choose it to be the one that minimizes this weighted 0-1 loss. Epsilon sub m equals the sum w sub I m times the chi of this condition of a mismatch. You calculate alpha sub m once you know the epsilon sub m, and then you can go and figure out what the next learner needs to be. So which model is best? All of them. Even the weakest learners can contribute. You can use multiple k-nearest neighbors. You can use many decision trees. You can choose the best and then boost with the rest. So it works best if all are wrong in different ways. In other words, you have independent errors. There are times, however, when the errors are not independent. That means we need more sophistication. So one way to introduce a more sophisticated approach is to use what's called bagging, bootstrap aggregation. Given a set of data, sample with replacement to generate m new versions of the data, m resampled versions. Apply the classifier or regressor to each new data set, aggregate, voting for classifier, averaging for regression across all m predictions to get a final prediction. It's what's known as a random subspace method. It's often combined with boosting. We'll see that in the next video. So, in general, we never use only one algorithm. Boosting many weak learners is better than a single parameter tweaking approach. Neural networks really use this idea to an extreme. But don't expect miracles. Complex data often leads to most classifiers making the same mistakes repeatedly. At least one learner must discover new information, and bagging often helps.